Hello, my dear students. I hope you are doing great. In the last video, we saw how to write relative velocity in different frame of reference, in translational frame, in rotational frame, as well as frame which is both translating and rotating. We know how to write relative velocity. Here, we are going to make use of that relative velocity concept which has been written in rotating frame of reference. Let's see here. So this is all about analyzing the particle's dynamics in a rotating frame of reference. So basically we are interested in writing Newton's second law in rotating frame of reference. Let's see that here a particle of mass m is moving anywhere in space and there is a frame. Here we are showing the frame. One is the k dash frame. I'm saying this k dash frame is rotating with angular velocity omega and angular acceleration alpha, right? I have shown it here, omega and alpha. This is your k dash frame. And the green one is the k frame. K frame is the fixed frame, right? And the origin, both the origin is coinciding, both the observers in k and k dash frame are coinciding, are at O. Okay. So now let us analyze this at time t. So here we are showing that Rin, which is the position vector of this particle in the inertial frame with respect to the inertial observer. Both the observers are at the origin O, right? So Rin is equal to ROT, means this is the position vector with respect to the rotating frame. Okay, rotating observer here. And this is equal to R vector. It means both these position vectors are coinciding. Okay, position vectors in the inertial frame and position vectors in the rotating frame are coinciding. Okay. So basically this frame is rotating, means what? The coordinate axis, this black axis will keep on rotating, right? Now we have already derived that if the frame is rotating with angular velocity omega, there is a relation between the velocity in inertial frame and the velocity in the rotating frame. So VROT is the velocity of the particle in rotating frame, right? So here I have shown this particle P has the velocity VROT, okay, with respect to this observer which is rotating. Okay, so this is the relation which we have already derived, which we have seen in great details. So velocity with respect to the inertial observer is equal to velocity with respect to the rotating observer plus omega cross r, which we have seen. So basically our agenda here is to prove various kinds of the pseudo forces which will be appearing in the Newton's second law equation as observed from k dash frame. Okay, so I'm going to prove it out. Let's see step by step. Many mathematical things are there, so we have to be very careful about it. Let's see here. So Vin vector is nothing but rate of change of position vector dr by dt as measured, as observed with respect to the inertial observer. Okay, is equal to, this is the velocity observed with respect to the rotating observer, means dr by dt with respect to the rotating observer, ROT I have written, and mark it at R vector is same for both the observers, and then plus omega cross R we have. Okay, now let's see here the acceleration of the particle A vector as observed with respect to the inertial observer, inertial frame of reference, is nothing but d by dt of Vin, right? This is the velocity with respect to the inertial observer, the rate of change of this velocity. Okay, so d by dt of Vin in the inertial frame. So that's why I have written it. This is with respect to the inertial observer, right? So rate of change of whose vector? Whose vector this represent? This represent velocity vector with respect to inertial observer. And I'm taking this derivative with respect to the inertial observer. We are writing A vector is equal to d by dt of, this is the velocity transformation in the rotating frame as this equation we have, which we have already derived, VROT with respect to the rotating observer plus omega cross R. Then A vector is equal to, take it, separately, you'll be getting d by dt of VROT in inertial frame with respect to this inertial frame. Okay, so the derivative is taken with respect to the inertial observer, and VROT is what? VROT is the velocity as observed with respect to the rotating observer. Okay. And then plus dy dt of, I'm writing it separately, omega cross r with respect to the inertial observer. So basically the derivative is taken with respect to the inertial observer. Okay. Now I am going to apply the frame transformation here for VROT. Okay. As we have seen that for any vector, we can write dy dt of any vector with respect to the inertial frame is equal to dy dt of that vector with respect to rotating frame plus omega cross that vector, right? This we have already seen in the last video. Fine. So here, what is this quantity? This quantity is dy dt of the rate of change of the velocity with respect to the rotating observer. And this entire derivative is taken with respect to the rotating observer. And this is nothing but acceleration of the particle with respect to the rotating observer plus omega cross that vector. And what is that vector? VROT. Okay. This is the frame transformation. For any vector, it is true. So here this vector is VROT vector, right? Moving on. A vector is equal to, this I have written. Again, this frame transformation I have applied. So this thing can be written as this one, which is AROT plus omega cross VROT, right? So I have expanded this term. This is your this term plus dy dt of omega cross r. You take this product rule here. You will be getting dy dt of omega cross r plus omega cross dr by dt with respect to which observer? Inertial observer, right? Again, I'm writing AROT plus omega cross VROT, velocity with respect to the rotating observer, plus alpha cross r. So this is d omega by dt is nothing but alpha. So we have this alpha vector cross r vector with respect to which one? With respect to inertial observer, right? Because this is your inertial observer. And plus omega cross dr by dt with respect to inertial observer, right? And this with respect to inertial observer, rate of change of this position vector with respect to inertial observer is nothing but velocity with respect to that inertial observer, right? Furthermore, so many terms are there. So we are analyzing all these mathematical terms here step by step. So now AROT I have written. This is omega cross VROT. Okay. Alpha cross R. Now one more thing here. This is alpha cross R. So RIN or ROT both are same, right? The position vector with respect to the inertial observer is equal to position vector with respect to the rotating observer, as we have seen over here, right? Both are same. So if these both are same, then in that case, we have this alpha cross R. I have directly written like this. Plus, now this term. And what is this term, by the way? Omega cross. This is VIN. Again, velocity transformation I'm doing. So VIN can be written as VROT plus omega cross R, right? For the velocity in inertial frame is equal to velocity in rotating frame plus omega cross R. And then we have taken this distributive property. So omega cross VROT plus omega cross R. I have written over here. And finally, we have like this term is, I have written this term over here, omega cross VROT, and again omega cross VROT. We have this 2 omega cross VROT. VROT means velocity with respect to the rotating frame. And then we have this term omega cross R. So many terms are there. So now I'm checking this AROT, acceleration of the particle with respect to the rotating frame is equal to acceleration of this particle in the inertial frame, and then take all these terms to the left side. You will be getting minus alpha cross R minus 2 omega cross VROT minus omega cross R we have, right? So I have taken to the left side. And then what I have done over here is to multiply it by mass of the particle, because we are interested in writing the Newton's second law, dynamics of the particle. So mass times acceleration with respect to the rotating frame is equal to mass of the particle times acceleration in ground frame, in the K frame, right? And this is nothing but the net force acting on the particle. This is all these real forces are there, right? So these real forces are net real forces is equal to mass times acceleration in K frame, in the inertial frame. Okay, and then mass times this quantity minus alpha cross R, and then again mass we have multiplied, becomes minus 2 m omega cross VROT, and then we have over here is plus m times, I have taken A cross B is equal to minus of B cross A, like that. So I have taken this to the this side and this one to the right side. So here different forces are there, right? So this is the real forces. So mass times acceleration with respect to the rotating frame is equal to net real forces plus these terms are there. Look at this. Mass times minus alpha cross r is known as the Euler force. This is one pseudo force over there, right? Like for the normal translation case, you know how to write the pseudo force. Mass times mass of the particle times x negative of the acceleration of the frame of reference. You know how to write. Likewise, these terms are there. Minus of alpha cross r. So Euler discovered this one. So on his name, we are calling it Euler force. Mass times minus alpha cross r. And then we have other force here, Coriolis force, minus 2m omega cross v r. And then we have this term is known as, this term, mass times, this term is known as the centrifugal force. Omega cross r cross omega, or mass times negative of omega cross r. Okay, both are equal only. These two are equal. So this term is known as the centrifugal force. We will see all these forces step by step. So now these three terms are basically the component of the pseudo forces. So let's see one by one here. First, consider centrifugal force. We will see the magnitude and direction of the centrifugal force. So let's see that this observer is rotating, right? And he's lying on the axis. Okay, this observer can lie anywhere on the axis. And with respect to this observer, this is the particle's position he's measuring, right? And position vector is r vector. So centrifugal force here is saying that minus m omega cross r, this term, mass times this or this, both are equal. So I have taken mass times of this term is the centrifugal force. Okay, so minus m omega cross r. And if we analyze this term, what is this term? So omega cross r, first analyze what is omega cross r. Omega is, you know, in along the y-axis I have shown here, and r vector is, you know, in this direction. Omega cross r will represent what? Omega into r into sine theta, and r sine theta is nothing but your r perpendicular. So r perpendicular means the particle's perpendicular distance from the axis of rotation. So omega into r perpendicular. And what is its direction? Its direction is going to be, you know, into, right? Omega cross r, omega to our curlier finger using the right hand thumb rule. And then if you take this omega r into the board means minus k cap I have written, and minus m into what is the direction of omega? Along j cap, in this direction we have. So if you do this, you'll be getting m omega square r perpendicular. And what is the direction coming out to be? So minus plus j cross k I cap. And you know, along I cap you are getting, and this is coming out away from the axis along I cap I have. So always remember that no matter where the rotating observer is, rotating observer can be here, anywhere on the axis, right? He can be here. The centrifugal force will always be m omega square into r perpendicular, and it will always be directed away from the axis. Okay, perpendicular to the axis and away from it. So what is its magnitude? M omega square r perpendicular. Okay, and what is the direction? Direction of the centrifugal force is going to be away from the axis, perpendicular to the axis, right? Now let's consider this next force. We have this Coriolis force. F Coriolis is, remember always, minus 2m omega cross VROT. VROT means if any observer which is rotating, if he sees that the particle has some velocity with respect to him, then there will be Coriolis force. Example, if you take a disc over here, and let's say there is a coin placed and coin is slipping on the disc, and observer here is rotating along with the disk with angular velocity omega. So here this observer will see the Coriolis force as well, because with respect to this rotating observer, he will see the coin is slipping with this velocity, which we are calling VROT. With respect to this rotating observer, we have this velocity. Okay, so what is the force here? Coriolis force is always, remember, minus 2m omega cross VROT. So if VROT is 0, means with respect to the rotating observer velocity is 0, it means the particle is at rest with respect to him, right? And then in that case, Coriolis force will be 0. And what is the direction of the Coriolis force? Opposite to direction of omega cross VROT. Then we have the Euler force. When omega vector changes with time, where alpha vector is equal to d omega by dt. In that case, Euler force, another component of the pseudo force will appear. And this Euler force, as we have seen, is minus m alpha cross r, right? We have seen over here. This is Euler force. Euler force. And what will be its direction? Opposite to direction of alpha cross r, right? Now, in general, if the frame is rotating with omega and alpha, and as well as it is translating with acceleration a naught. For example, this frame is rotating with angular velocity omega and angular acceleration alpha, as well as, let's say, this frame is also translating in some direction with acceleration a naught vector. In that case, now one more component of the pseudo force will come into picture. So what is that? This is the translational component will be coming up, right? Which is, what is value? Its value will be minus m a naught vector. And this is pretty simple one, which we have already been seeing how to write, in the translating frame of reference. So what will be these forces? So this is the real force. Okay, this real force plus this pseudo force. So 4 components of the pseudo forces will be there. 3 rotating components, and another one is going to be the translational component of the pseudo force. So this real force plus the pseudo force is equal to mass times acceleration of the particle with respect to this frame, which I have written a relative. Now let's see this application in action, right? So how we are going to apply all this very, very essential thing, because this is the derivation we have done. And derivation is equally important, because if you don't understand the derivation, you probably won't be able to apply it. Let's see these questions, illustrative problems here, beautiful problems, how we can apply these in various situations. Okay. So first example, let's consider the centrifugal force only. Okay. See here, a coin rotates on circular table without slipping. Okay. This is the coin you see is rotating on this circular table without slipping. There is enough friction. We have to write NLM with respect to this rotating observer, rotating with same omega as that of the disk, and he is centered at the origin. First analyze your frame. Which frame is this? Obviously the rotating frame. Alpha is 0, right? So Euler component will be 0. So you have to identify, okay, Euler will be 0. Euler 0. Fine. What other will be 0? Coriolis will be 0 or not? For Coriolis, V rotating should be there. But this observer will see that the coin will always be stationary, right? So all the time this coin will be facing towards him like this. So again, Euler component will be 0. Then Coriolis will be also 0, right? There is no translation. So translational component is also 0. Then we are left with the centrifugal force. Only component of the pseudo force will be the centrifugal force. Let's see the centrifugal one. So here, with respect to this observer, what are the forces he will be seeing? One is the centrifugal force. We know the direction of the centrifugal force is always m omega square into r perpendicular. And r perpendicular is the perpendicular distance from the axis of rotation, which is capital R over here. Okay, so this is the centrifugal force away from the axis. So away from the center. And then this is the static friction appearing, right? So static friction direction will be opposite to the centrifugal force. Why? Because this guy will see that net force is 0, right? Because here the coin is always stationary with respect to him. So I can say that here Fs minus m omega square r will be 0, right? So Fs will be equal to m omega square r. Pretty simple. Isn't it? Now with respect to the ground observer, if we write the Newton's second law, we will be getting what? This, with respect to this ground observer, we'll see that only force acting is the static friction, right? So FBD of this with respect to this ground one will be Fs here. Only Fs will be there. And force is equal to mass times the acceleration towards the center, which is a centripetal. Centripetal acceleration, and centripetal acceleration is omega square r. So Fs is equal to m omega square r. And we are getting the same equation from both the frames. Okay, now note here that the real forces are frame independent quantity, obviously. So this static friction will be same with respect to the ground observer or the rotating observer. And we are getting the same equation only. Fs is equal to m times omega square r. Here also Fs is equal to m omega square r. Okay. If the rotating observer is rotating with same omega and lying anywhere on the axis, centrifugal force would still be same, as I have already mentioned. No need to explain this one. I have explained it already. Okay. So if this observer is lying here, anywhere on the axis, he will see the centrifugal force as the same, m omega square r only. Okay, because m omega square into r perpendicular we write. Okay, don't write this distance from the observer to the coin's distance. No, only write the r perpendicular. Fine. This is example one. Moving on to example number two. I'm taking the case where centrifugal and translational component of the pseudo force is there. Okay, means Coriolis and Euler component of the pseudo force is absent. Now, consider this example. Here we have this coin, and coin is kept here. It means sufficient friction is there so that it rotates with the same omega as that of the disk. And there is an observer fixed on the disk. Yes, this observer is fixed. Means this observer is what? Is rotating with the same omega, right? So now we have to write NLM with respect to this observer. Let's see. So here, first analyze this frame. Is it only rotating frame or the rotating plus translating? We have to see. We have to check whether this has some acceleration or not. So this observer, if you see that this observer will have acceleration towards the center because it's fixed, right? And his acceleration is the centripetal acceleration, which is nothing but omega square into r naught in this direction we have. Okay. So we can say that this is the rotating observer as well as the translating one. He has some linear acceleration. He has omega square r naught. So we can say that here this guy will see that the centrifugal force, okay, centrifugal force, this guy will see, fine, m omega square into r perpendicular. Oh, which one is this r perpendicular? R perpendicular is this distance, perpendicular distance from the axis. Whose axis? Axis of the observer. So this is the perpendicular distance. And away from the observer here, right? So that's what I have written here. Look at this. So let's say this position vector of the coin here. This is the coin position is RC vector, right? Given in the question. And this is the observer whose position vector is RO vector. So I can say that RC vector minus the RO vector is this vector, right? This vector. So what will be the centrifugal force? M omega square into this vector, right? Yes or no? Because M omega square into R and direction is away. So I can write this only. RC vector minus RO vector is this one. So that's your centrifugal force. And what is the translational component of the pseudo force? Is m omega square r naught vector. Okay. Why m omega square r naught vector? Omega square r naught is the magnitude of this acceleration towards the center. And r naught vector I have taken away. So we know the translational component of the pseudo force is minus m times acceleration. And acceleration is in this direction. If you take this minus, so you'll be getting in this direction, right? So that's what I have written here. This is your minus m times acceleration of this frame, m a naught. So minus a naught is omega square r naught vector, right? This is what I have written. And fs vector is the static friction, which is the real force. And note that the Euler component will be 0 because alpha vector is 0. No Euler will be there. No Coriolis will be there because this observer will see the coin all the time at rest. So VROT will be 0. So with respect to this observer fixed on the disk, he will see no acceleration because he will see all the time the coin to be at rest. So A relative is 0 means net force must be 0. And if net force is 0, I can say that what are the forces acting here? He will see the force is acting Fs, F centrifugal, F. This is your translational component of the pseudo force. So all these three forces sum will be 0. So Fs vector plus this centrifugal force is m omega square into Rc minus R naught, and translational component is m omega square R naught vector, right? And if you do this, add this two, this will be cut. M omega square R naught will be cut. So you are left with m omega square Rc vector over here, which is independent of the position of the observer RO vector. So Fs vector I can write m omega square into minus Rc vector. You see, minus Rc vector. Well, so this is the static friction is equal to m omega square into minus Rc. Minus Rc vector means Rc vector is in this direction, minus Rc in this direction. So static friction value is equal to m omega square into this distance. Okay. Rc is this distance. And this equation will be exactly the same as observed by the which observer? The ground observer. The ground observer, you see, he's writing this equation. Static friction is equal to mass times the centripetal acceleration. And the centripetal acceleration is omega square into Rc, right? towards the center. So Fs vector is m omega square into minus Rc vector, because Rc vector is this one, right? So that's why it's minus over here. So these two equations are, this equation and this equations are identical. You see, the same equation we are getting, right? So now basically we are getting the feel of how to write this NLM equation with respect to the rotating or the translating observer, right? Next one. I'm taking the third example over here. Third example, I'm taking all these illustrative examples just to get you feel of how to write this NLM equation. So you see, this disk is rotating with angular velocity omega, and there is a coin outside the disk lying on the ground. And observer is rotating with the disk at its center. Yes, observer is standing here. He is rotating with the disk. He is fixed at the center, rotating with the disk. Again, we have to write NLM equation for this coin with respect to this observer. Let's see now over here. See, if you imagine that if you are rotating in this direction, right? You are rotating in anti-clockwise sense. And there is a particle which is lying on the ground. Will you see the particle to be at rest? No. You will see the velocity of this particle to be how much? Your omega times this perpendicular distance r, right? But in which direction? In opposite direction. Because you will feel that the coin will rotate opposite to your direction. So if you are rotating in anti-clockwise sense, this coin will appear to be rotating in clockwise sense. So there will be the VROT, means velocity with respect to the rotating frame is equal to omega r observed by rotating observer. So the centrifugal force is equal to m omega square r. Yes, we know, away from the center, away from this observer. This is our centrifugal force. Then we have the Coriolis force. Now there will be Coriolis force, right? Which is minus 2m omega cross VROT. And if you do, F Coriolis is going to be equal to how much? Minus 2m. Omega direction is omega k cap, right? This anti-clockwise, omega k cap. VROT direction you see, minus j cap direction you have. So it's coming out to be, minus coming plus 2m omega VROT. K cross j is minus I cap. So Coriolis force is minus I cap, means in this direction you have. What will be its magnitude? 2m omega into VROT is omega. So 2m omega square r. So you have the Coriolis force as 2m omega square r, right? And there will be no Euler force here and no translational component because this is only rotating. So now one more thing, with respect to this observer, will he see acceleration of this particle? Yes. Acceleration won't be zero. There will be some acceleration. And what will be its acceleration? Since he will see that the particle is going to rotate in which direction? In this direction, right? He will see that VROT. So VROT is changing its direction. Okay. So right now VROT is here. After some time VROT will be here. So the direction, due to this direction change of the VROT, velocity of this particle with respect to this observer, there will be one acceleration component towards the center. You know, this centripetal acceleration is due to the change in the direction of the velocity of the particle. That's what this observer will see. That centripetal acceleration he will be seeing. Towards him he will be seeing, right? Because of this change of the direction of VROT. So what will be the acceleration? V square by r he will be seeing, right? So VROT square upon r. Because VROT is changing its direction with respect to that observer. So net force is equal to mass times acceleration with respect to him, which is V square by r. VROT square by r. So what are the net forces from the FBD? You see these two pseudo forces are there. F Coriolis minus F centrifugal is equal to m omega square r, right? And VROT square by r is, VROT square by r is nothing but VROT is omega r. So I'm writing m omega square r. So F Coriolis minus F centrifugal force must be equal to m omega square r. Okay. Then we can say that he is going to see this one, this net force towards the center, which is Coriolis force minus the centrifugal force he will be seeing, right? And then we have these two forces already computed, centrifugal and the Coriolis. If we subtract this, Coriolis minus centrifugal, what is the Coriolis minus centrifugal? Second equation minus the first equation. Coriolis is 2m omega square r, we have calculated, and this is m omega square r, centrifugal force, which comes out to be m omega square r, and which is the same. Here also we are getting m omega square r. So this is consistent, right? So this is your example number 3. And in the next video, I will be taking up example number 4, which is the general one, because the observer is rotating with angular velocity omega naught and angular acceleration alpha. So I'll be taking this up in the next video. Otherwise, the video is going to be long. So I hope students, you got all the points clear how you are going to apply Newton's second law in rotating and translating frame of reference.